All righty. Happy Monday, everybody. My name is Daniel Dramoni. I'm the president of the Washington Capital Area of ICEAA. Thanks for joining us today during your lunch break to talk about sustainment analysis methodologies and cost models for business cases. Our speakers today are George Bayer and Austin Luderbach from Kobeck Consulting. I think I've gotten a preview of this briefing. I'm, as a ONS SME myself, I think ONS doesn't get enough attention. And so I'm really happy to be able to talk through a bit of it today and look at some, what I think are really impressive models and techniques for that Kobeck's developed for the FAA and that they utilize for to support their investments and decision making. George Bayer is the senior director at Kobeck and leads a team of consultant analysts in developing cost and benefit models and business cases for FAA acquisitions. He's got his MBA in corporate finance from University of Texas, Austin, and undergraduates from the University of Florida, as well as a PMP certified professional. With over 20 years of finance in this field, he's well suited to bring subject matter expertise to the problem, which he does over there at Kobeck, leading his analysts in support of the FAA. Who make lots of important investment decisions in order to keep our aircraft in the air and us flyers flying. It takes a lot to keep the skies safe and airports safe, and so we're going to get to hear a little bit about the decision making that goes behind that from George and his team today. Austin will also be briefing a bit, although he's feeling a little under the weather, so he might not speak as much as we might like him to. Also an analyst at Kobeck Consulting, Austin has a BS in mathematics and statistics from Purdue and a master's engineering from Cornell. I think having seen the presentation, I think Austin really brings a lot of sort of the more modern data science type tools and techniques to bear, along with the SME knowledge that George and the other senior folks provide. And so you'll get to see some of those more modern techniques put to work here, which I think is really exciting. After the survey after the discussion today, there will be a quick survey along with some chapter announcements. Please hang around, take the survey. It's really important to ensure we can award a end of or a year Speaker of the Year award. And so please, and also it helps us know if we're giving you, our chapter members and the greater ICEAA community, the types of presentations you're looking for. So please stick around to the end and take that survey. Without further ado, though, I'm going to stop screen sharing. George, I'll hand it off to you and Austin, and looking forward to the presentation today.
Thanks, Dan. Go ahead and share my screen. As Dan mentioned, we'll be talking today about sustainment analysis methodology for cost models and business cases. And there's a lot of infrastructure investments in the government today that are aging in the FAA. We call it the national airspace, that need to be maintained, and estimating when that end of life and the end of service of those systems happen and how those impact costs are really critical for the agencies. So we'll talk a bit about that, and we'll have an FAA perspective, but this is something that can be applied across multiple agencies in the government as well. Jump ahead. Okay, so we will first talk a little bit about government capital investments. Then we'll go into a failure analysis and talk about infrastructure investment specifically. We'll talk about sustainability analysis and business cases and how we estimate end of life of systems and the timing of that replacement and why that's important. We'll talk about sustainment costs and the repeatable process that we can create that impacts stakeholders and how it impacts those stakeholders. We'll talk specifically about the FAA stakeholders and how they make investment decisions. And then we'll talk about some of these cost drivers that we can, that impact our cost models from sustainment analysis and failure analysis. And then we'll show the methodology. We'll talk specifically about the methodology that we used in our models and what kind of models we did and why we created those and some of the results. So let's start in the first part here. So government capital investments and legacy infrastructure. So starting out, the federal agencies try to sustain large infrastructure systems, usually much longer than they intend to. much longer than the life cycle intention. And so we need to find ways to sustain these existing systems. The FAA often keeps systems sometimes 20, 30, 40 years and much longer than they originally intended to be. And as these new technology systems need to be replaced, they do partial tech refreshes of those systems. So we need to understand when and what the scope of those tech refreshes should be. The critical components in understanding that is parts failures and demand analyses. So conducting this demand analysis and forecasting into the future. We need to understand inventory as well of these parts. So how long can we keep things going, and can we continue to procure those parts? And then we need to have some sort of system in place, a sustainment model that allows us to evaluate these systems and sustain them in a repeatable process. So the way that we've come up with this, we've come up with 3 major models, and we'll go through these later in the presentation here. The first one is a large scale model, and this helps us identify those high risk parts that kind of drive the end of life of the system. Allows us to focus in on the problems. And then we have a deep dive sustainment model, which looks at those specific risk parts, high risk parts, and we analyze to determine when that end of service might occur, how much time we have, and what kind of risk mitigation that we can do. And then there's a sustainment procurement model, and that's ability to come up with some of those risk mitigation solutions. And we'll talk specifically about those as well. So government capital investments. The FAA, like some civil agencies, requires business cases to be justified in order to get funding. So it's not just, hey, we're going to go ahead and work on, create this project. The agency needs us to justify it with a cost benefit analysis. So we develop our cost estimates, but we also develop a shortfall analysis, determine what is the shortfall, how do we quantify that, and how do we monetize it? And then what are the benefits? And in the case of the FAA, the benefits are a little bit more altruistic. We're looking at benefits to the FAA itself, efficiencies, cost savings, and also benefits to the airlines and to the flying public. We monetize direct operating costs for the airlines and passenger value of time for the public, flying public. There are 2 different types of investments. We look at new investments that have new capabilities potentially, and we look at infrastructure sustainment. So these are systems that we already have in place, like radar systems that the FAA has. And how do we sustain those systems until a replacement can be bought, procured, or developed? And we evaluate these business cases with some finance metrics. So a net present value greater than 0, internal rate of return, and payback, and what we call a BC ratio. That's ratio, not ratio. And the BC ratio is your discounted benefits divided by your discounted cost, and should be greater than 1. So for these large infrastructure investments, we need to be able to have established criteria to justify the investment. And what we look at first is the historical parts failures to estimate what the future parts failures would be. And so we can understand what the demand for these parts, because running out of these parts, exhausting existing inventories or finite inventories, is usually the cause of the obsolescence or the loss of service, potential loss of service. And we want to make sure we're ahead of this. So if we can estimate of a certain year that we are vulnerable to loss of service, that we've run out of these parts, these finite parts, then we want to get ahead of that and have the investment occur a few years prior. And we also want to understand what the impacts are. I think investment planning and analysis in an evaluation group within the FAA that says, so what? And so we evaluate what the impacts are as well. And sometimes there's a safety risk. We could have a loss of service of a radar system or a particular FAA system that could make the FAA vulnerable, the flying public vulnerable to safety risks that they previously did not have. So this analysis and this forecasting and understanding our parts demand, the inventory parts, and when we would run out is really critical service for the agency and for timing of that. When we look at parts failures, and that's really our first part, there's this sort of theory, but a lot of parts kind of follow this model, and it's called a bathtub curve. In the early phase of a bathtub curve, there are a disproportionate number of failures at the beginning of time. And that's because you're starting up a new system that hasn't been tested. And so it has a disproportionate number of failures at the beginning, but then they level out over time during that mean time. That's usually the longest period of time. We have a level number of failures that will increase over time slightly and start to increase. And then what you're trying to predict is when has the system reached its end of life, when it can no longer be sustained and things are disproportionately going to start failing all at the same time. And that's the back end of the bathtub curve. We want to try to avoid that or being caught too far into that. And we want to estimate how many failures we're going to incur to exhaust our existing inventory. So we mentioned the two different types of investments, the infrastructure and the new capabilities. And so we want to evaluate the condition of the existing operations and their components. We want to understand the sourcing requirements as we set these investments up and try to sustain them. And we want to conduct an inventory analysis of the spare parts. Other things that we need to consider are the supply chain. How do we distribute parts into the NAS? Are there any kind of bottlenecks or constraints that we have? And when we're looking at these investments, sometimes we can't afford everything. So are there some of these investments mutually exclusive? We have to choose which one is more urgent. These are all things that we need to understand when we are proposing infrastructure investments and the timing of those investment decisions. And there's 5 major cost considerations. So we need to understand how much it costs to sustain the existing system, and that we call that a legacy case. It's part of the legacy case. If we continued operations, how much does it cost to sustain that? And we need to understand, how long can we sustain this, or can we sustain it at all? At what point in time will we no longer be able to sustain the existing operations? What's the cutoff point? And kind of back into that one. And then what kind of methods do we have to potentially extend the life? So if we think that we will run out of parts in 2025, what kind of sustainment methods could we have to extend that another couple of years? And then we do a cost benefit analysis to justify that investment. Some of those objectives, estimating the end of life, these are our sustainment analysis objectives. We need to understand what is that date when we can no longer sustain it, and when would we potentially lose service, and what is the best time to invest. You might be able to get the capital dollars in 2024, 2025, 2026. What year do you actually need it the most, so not to take that money from another program potentially? And what kind of trade-offs do we have with other programs as well? And then means of evaluation, that's what we're focusing on today. What's a repeatable process that stakeholders can use to make these evaluations and compare programs? As we look at our decisions and our data impacts, the FAA has some challenging data for demand data. And part of that is the demand data is based on parts orders. And parts orders are not necessarily consistent with the parts failure timing. So we don't actually record within the maintenance world the exact time or date or location of the part failure. That data becomes available to the logistics center when those parts are reordered for the NAS to backfill inventory. And the timing difference causes our data to become choppy. That the issue is we do not predict correctly what our forecast, when the frequency or the volume of those parts failures, it could impact our forecast of the timing of the investment. If we invest a little too early, that means that we're potentially taking a limited amount of capital that the FAA can invest, about $3 billion a year. We're taking some of that capital away from another potential program that they have to be delayed. So a lot of these things are mutually exclusive. If we invest too late, then we're risking loss of service of the system, which has potentially safety consequences and other consequences as well. So we want to make sure we're as accurate as possible. So here's the major factors. And now we're really kind of getting into what we're evaluating. When we're doing this end of life estimation and estimating the time of the potential loss of service, these are the main factors that we need to consider. We first want to estimate the rate of failure, how many parts are failing each year. And then we want to do a trend analysis forecasting. We do regression to do that. And so we forecast out failure growth rates. And then for some of our parts, and I'll talk about this in the next slide here, but some of our parts are called exchange and repair. That means that these parts are sent in when they fail to a depot and are repaired and then put on the shelf serviceable for the next part that needs to be exchanged. So that could be an endless cycle of recycling your parts, but some of those parts cannot be repaired, and that's called scrap rate. And that scrap rate is very, very critical because that's how many parts are actually depleting inventory. So that gets us to the next point. So we look at how frequently those parts fails and how much those failures increase over time, and what failures that we cannot repair. And then we analyze that and compare it to the inventory. We have a starting finite inventory, and how does that deplete over time? And if we deplete inventory, can we just go ahead and buy some more? Or at some point in time, are those parts no longer manufactured and we cannot procure them at all? And then what other options do we have? Can we substitute that with a like-for-like part, and which needs to be tested out? Those are things that we need to consider. From a cost modeling standpoint, there's three major cost estimates that can be derived from a sustainment analysis. One is the annual part procurement to sustain. So if we can estimate the volume of parts that fail each year and that need to be replaced, and we have unit costs for those parts, we can estimate pretty accurately what we think that each year's procurement cost would be. And then from our corrective maintenance, if we understand the frequency of those failures, the frequency of the part failures, how often the maintenance team needs to go out to the site to make a repair, we can estimate corrective maintenance from that. And then the preventative maintenance would be the frequency of going in a preventative way, a proactive way, and making assessments of parts and making repairs prior to the actual failures. And each of these can be estimated through our modeling. I mentioned this here. Each organization will have specific stakeholders that are trying to make different decisions or be informed from this data set. So the logistics center of the FAA is trying to estimate how many parts that are returned broken, that are repairable, how many of those they need to repair. They have about half their inventory is repairable inventory, and they can't fix everything at once. So they have to decide what they're going to fix upcoming year. So if they have an estimate about how many parts are failing, they would know how many parts they need to repair. So that accuracy is very important to them. Otherwise, they're kind of doing fire drills and chasing their own tail if they get surprises about what parts are failing that they did not anticipate. The program management organization is trying to use sustainability analysis to determine what systems to replace, when do they need to do a new investment or replacement investment for that system, and when they need to start that investment analysis process and development work. And then the capital investment team is deciding between all these different programs, asking for a limited fixed F&E budget and how much money they're going to give to each program and to whom. So these forecasts of when the timing of those investments really comes from the sustainability analysis. We also have some cost drivers here that we need to consider. So outside of the parts failures and inventory analysis, there's some other factors that we need to consider when we're updating our cost estimates from this. There's the cost per maintenance action. So if we know the frequency of the failures and how many times they go out there, we need to understand how much it costs to make that maintenance repair. What is the labor cost? And then the analyses. For the investment timing, again, this is going to influence that analysis, and that historical failure analysis helps us to determine that urgency. Oops, way down here. And then for parts procurement and storage, there's a cost per part to backfill parts for procuring those parts. What is that estimate of cost? And sometimes there's a volume discount. How much does it cost to store those parts? And then what is the cost of distributing those parts? How do we ship those parts out to the national airspace in the FAA's terms? And the time to repair, calculating that mean time between failure and that inventory depletion, obviously allows us to time phase our cost estimates. And then what kind of options would we have for mitigating risk, and what's the cost component to that as well. So we're going to switch here to our cost methodology. And what did we do to analyze this, and how do we build our sustainment model? So in our failure analysis methodology, we first are looking at what are the parts within the system. So if we have a new system, infrastructure system out there that we're analyzing, we want to understand what are all the component parts, what are the parts that we spare for that system, and making a comprehensive list of those parts. And once we have that, we're going to separate them all and categorize them into low, medium, and high risk. And they're defined in this way. So the low risk means that, you can go out and buy those parts. Each year you can go out and buy the parts that have been depleted and restore your inventory of your supply. Medium risk means that there's supplier risk, that perhaps you had 5 suppliers originally, now it's one final supplier, and you don't know when they're going to stop manufacturing that. So it might be some consideration to do a lifetime buy before that supplier doesn't exist. And then the high risk would be that there's no supplier available at all, and the number of parts that you have in inventory, that's it. And so those are really the high risk ones we're going to focus in on. So our first step is to do a failure analysis. And we use historical demand, and the more demand, number of years of demand that you have, the better. So you use historical demand, gather that data, and start analyzing those parts. And you can see in the graph on the right here, this is some choppy data. This is how it kind of comes in from the FAA, from the parts orders. But that there's a trend line that we could draw on this, and you could use moving averages to make it a little more precise. We did in this case, we have a linear trend line, fit line here. We use some regression analysis, and you forecast out how those failures would be sustained going forward. We do put a couple limits on this because sometimes it gets a little exponential. So we don't want to have any future demand forecast that exceeds a third of total inventory turnover. So those are some of the limits that we put on there when they really start getting enormous. But this is critical of forecasting out using historical data to forecast out your future failures. Another component of that we mentioned with the exchange and repair parts is scrap rate. And sometimes it's difficult to get that scrap rate. We'll talk a little bit about that. But the scrap rate is how many parts can we not repair for the percentage of the ones that come back for repair and exchange repair. And that's when it becomes a 1-for-1 inventory depletion. And then we collect the inventory counts. So we have a starting point, and we're going to forecast each year how that inventory changes over time and is depleted. And then we really need to align our forecasting with how long do we need to keep this system going. So if we want to keep this going to 2030, then we want to analyze if we're going to run out of parts within that period of time before 2030 or not. And we'll look a little beyond it as well, because sometimes our forecast could be off. If we do a sensitivity analysis, it could bring it back in within that same time horizon. And then we forecast out those annual inventory procurement of parts and the annual estimate of depletion of that inventory. How many parts do we need to go procure? We can't procure them. When do we become negative? So in our analysis, our sustainment analysis, we conduct this life cycle analysis. We assess the current inventory levels that are at the logistics center. And so we were really focusing in at the inventory that's centralized for distribution. I know different agencies might do this in a different way, but the FAA has central inventory to distribute across the NAS. They also have local inventory levels, which are not necessarily accessible on a consistent basis, and the transparency isn't quite there as well. So we're really focusing on the centralized inventory distribution. And then we compare that inventory versus demand levels. And then we estimate the full amount of inventory that we need to reach that end date. And at what point in time are we forecasting that we would deplete that inventory? From a cost standpoint, using the same number of of parts that fail that can no longer be repaired, so that inventory depletion, when we backfill that inventory from a procurement standpoint, we can take that volume and multiply times the unit cost for each part's unit cost. And then we can forecast out an annual budget for that. So there's a two-parter here. We're estimating that end of service date, and we're trying to update our cost estimate with a consistent procurement cost. And then the corrective maintenance really is just the frequency of those failures, not the parts depletion, but the failures, and how often we go out to the site to make those repairs. And we're multiplying that times the cost of labor to make the repairs. I mentioned scrap rate, and this is one of the potential pitfalls that they can have if you don't analyze in the right way. So the FAA, more than half of their parts are repairable. And so again, they send them back and they exchange a part. They say, I'll have a part failure, give me one that's serviceable, and I'll give you a broken one. And then the logistics center at the depot will make that repair, or they'll outsource that repair. And they'll take those repairables and convert them over time to serviceable. When they do test those parts out, the challenge is that they don't necessarily test that part as soon as it comes back. They test the part when they need it, if they need some of that repairable inventory to be serviceable, so they can have enough inventory to ship out. Then they'll test them out as they try to make the repair. And for the ones that they can't repair, then they'll determine that is scrap or beyond economic repair. And in our data, we often get cumulative scrap rates, and we have to compare that versus the number of parts that were attempted to be repaired, not the number of parts that were returned, but the number of parts that were returned that were attempted to be repaired. Otherwise, we could artificially estimate a higher scrap rate than it actually is. So we want to measure this as accurately as the data allows. If we have a cumulative number, you want to understand how many were attempted to be repaired. And then this is where it becomes more creative, and this is where a lot of the data analysis comes into play. Austin, would you want to jump on this part here?
Yeah, sure. So this is the large-scale sustainment model. And so what this does is it kind of scales the analyses that we talked about previously to a larger universe. So rather than handpicking a select few of parts, for example, and having to do all this work yourself, this model here will basically do all these analyses automatically. And so how it does that, it doesn't just do this with magic, right? We're not just waving a wand here. So it requires data, right? And if any of you have been to the recent ICEAA conference, you'll notice that there are a lot more panels on data, right? So there's a real movement going on utilizing data to its fullest extent. And so that's the goal of this large-scale sustainment model. We have these giant reports of the depot where these parts get sent to, and we have various information on these parts. And they're not just handed to us on a silver platter. Like, we don't just have these nice annual historical failures to us. We have to do some grunt work, pull up our sleeves, and kind of get into the data a little bit and get messy. And so that's kind of where that data engineering aspect comes from, right? So we have these reports, and we're trying to extract the nuggets of gold in it. So it's a lot of just big columns of like 40,000 rows, 100,000 rows of just a bunch of entries. And just as a whole, it looks like, just a bunch of mess. But if you pan enough through it, you can find your nuggets of gold there. And that's what the data engineering does. So we're getting the useful information from these data sets that can help with the analyses. And so that starts with some detective work. You have to understand your data set. But then after you've kind of done your detective work there, you can start to build a pipeline for this and start just feeding that data into the structure you build, and that'll output the nuggets that'll do the panning for you without you doing it yourself. And so once you've got that, once you've got your useful data, what we can start doing now is understanding what this useful data is telling us, right? So if we have historical failures for a part, for example, we can understand how that part would likely behave in the future, right? So just as if you're practicing tennis and you're wanting to learn how to play tennis, if you serve it and it goes a little too high, or if you serve and it goes a little too low, you adjust your aim and your power and et cetera until you get it just right. And it's a similar process for the model here. In fact, it will overshoot, perhaps on the prediction, may undershoot, but there's a certain sweet spot with how those failures are going to grow or behave. And that's what this model does. And so it finds that sweet spot, that perfect serve, and it will use that information to tell you how these failures are going to behave in the future, right? Based on that data that we've received. And then lastly, what we do with this information, the real value added is, well, okay, so we know that we're going to have these failures. What is that going to do, right? And George mentioned earlier about scrap rates. And so that is kind of the real driver there, because if you have a part that fails, if you have a keyboard or something and your U on the keyboard fell off, well, of course, that's not going to cause chaos, right? You don't have to burn the building down for that. You can just put another keycap on. So many of these failures are repairable, right? But others are not. You have to scrap it, and that's where you're going to start seeing issues, because you're not going to have a part being available for use potentially. And so the parts being scrapped, that's what's going to really deplete your inventory. And that's what the inventory simulation does. So we have, again, from the data that we've received, these reports, we have these inventory records that we refer to, and we look at how our forecasts, how our model, what our model thinks is going to happen, and we reconcile that with the current inventory, and we can get a snapshot into the future of like, okay, if we just let things play out and didn't do anything else, what's going to happen to our inventory levels? And well, you could see like, oh, for example, this part is this processor. If we keep things going as is, we may not run out of inventory by 2024, and that'll cause problems for XYZ, right? And so the real novelty of this, again, is that we're doing this at a large scale, right? So it's some programming involved, and some mature programming involved to kind of grow this out to the scale that we're working at here. And so it's able to do this. And I think when I run my model, it takes just 2 minutes. So it outputs these results. And that provides us with a list of potentially critical parts that, maybe raise a flag to you. May not necessarily guarantee it's going to be a problem, but it raises a flag, and that can allow it for further investigation.
Coming off of mute
George, I
here.
think you're muted. Yep.
Yes, I'm off now. So this is the large scale model. So this is something that's scalable, and that Austin created within using Python algorithms, so that it uses the historical data to forecast out the regression and the inventory, the demand data, and incorporates a scrap, and then simulates that inventory depletion. We have another model that goes into that. It's the deep dive model. Essentially, after we identify those high risk parts, we can really kind of look into other potential impacts of demand and other sensitivities, and adjust those numbers for accuracy and for the details on that. So the large scale, the great part of that large scale model is that it's you can have a very large data set, and you can identify all the parts that are really going to drive the end of life of the system, and then focus in on those. So from our large scale model, we get that list of the high risk parts that are going to drive the end of life, and this is the kind of outputs that you see is at some point the full depletion of the inventory and the negative cumulative inventory that would estimate the number of parts that we need to procure, if we have a means of doing that, to be able to reach our target end date. So the large scale model is the creative Python driven, ingest large sets of data, and it helps us to focus in on our deep dive. And then we use other techniques of other sensitivity analyses with their main driving factors to determine what this potential procurement needs, and which parts are driving end of life, and what the timing of those are. I'm going to hand it back over to you, Austin, if you want to close this out with the three models.
Yeah, sure. And just kind of as a side note, that this is not like a silver bullet that will solve all the problems, right? So this is the kind of the goal of this large scale sustainment model, is to reduce the problem set of like looking at, let's say 40,000 parts to maybe only a couple hundred or something like that, right? So you just, it's kind of, again, finding those parts that aren't going, that are maybe the primary troublemakers. And it doesn't replace that in-depth analysis. That's part of the pipeline that we see here. Is we have some deep dive models that's very handmade and not automated. It's taking coordinated with engineers and stuff like that. So by no means is this a replacement of that. It's just to help speed up the process, help get those identifiers, and make life easier in general for that. And so going forward here, this is kind of part of that bit here, the mitigation of those high risk parts. So once you have your list, you need to kind of look deeper, right? Like what's actually causing these problems, perhaps, right? It could be purely from a failure standpoint. So it's purely from you just have a high failure rate, you have a lot of operating service, you have a high scrap rate, and you have maybe low inventory, right? So that can be a potential explanation. There could be other explanations, such as you have another part that is starting to go end of life and it needs to be substituted. This other inventory piece needs to be utilized for that part to keep it going as well. So that's depleting. So you're substituting one part for another and it's depleting that part's inventory. And so that's kind of where the handmade work comes in, and the detective work. And other things you can do, as well as if we talked about those previous metrics, the sensitivity of our key metrics, such as like the scrap rate, for example. You can see, well, maybe what if scrap rate gets worse in 5 years from now, right? How does that impact our forecasts? And so we look at also how those forecasts may change over time if some of our key assumptions on our key metrics were to change. And so with all of this combined, you can kind of get a full picture of what are both the, in your face costs. So how many failures are you getting each year, but also potentially other latent costs, such as, specifically with the FAA, the passenger value time, like if the system's out, how long people have to wait, et cetera. Is there anything worse than that? So you can kind of get the full picture of how much risk is this part adding to your universe that you're operating in. And then that can help you strategize mitigation techniques. Do you need to buy more of these parts? Can you use another part that would be a one-for-one replacement that has plenty of inventory, right? So it allows you to, it opens up more avenues for you, and it allows you to explore your options and get to that point in a faster amount of time, quicker amount of time.
And one thing we've observed from data in some of these cases of the high risk parts from the scrap rate standpoint is that scrap rate does not stay. It doesn't really have a very projectable curve of its increase over time. What actually happens is that when we start encountering higher scrap rate, usually the component pieces that are used to make the repairs are becoming scarce. And if we can no longer procure those component pieces, then when parts start coming back for repair, say they have different component pieces that have broken, you can take two parts that come back, maybe cannibalize them together to make one repaired unit of that part. And so for every two parts that come back, maybe you can have one repaired version. That's an instantaneous 50% scrap rate. And that we have observed in multiple cases in current state, or that that they anticipate would happen in the next 2 or 3 years, when you have systems that are out there for quite a long time. That is much more likely to occur. And some of our other options about risk mitigation, you can do a like-for-like replacement in a system like the FAA, but it could take 9-12 months to do full system tests about the impact of that system, that new part. That might be more modern, that might mess something up several steps away in the software or in another hardware system to which it connects. So they have to test it out pretty thoroughly. So we do need lead times, and there's no guarantee a like-for-like replacement would work. And then you can also cannibalize, say another agency is getting rid of their ancient CPUs, then you might be able to go to cannibalize those parts from that other system that's being decommissioned and add to your inventory for a period of time and extend the life of that system. And we've done that before in the FAA as well. So those are some of the risk mitigation techniques for the high risk parts to help you to get to your point of the new investment that replaces it. So at the kind of conclusion here, we have developed a backbone of this sustainment analysis with three primary sustainment models. We have the large scale model, which Austin talked about, where he has the algorithms there in Python that we can take large data sets for all the parts in the universe for a particular system out that the FAA has in the NASA or any other agency you might have, and be able to identify which of those parts are high risk. We model out the part failures, the part failure growth, the scrap rate, and the inventory depletion over time, and estimate which ones are potentially at risk of a full depletion. Then we have a deep dive model where we add other factors and sensitivity analyses and really dig into some of those sources of procurement and demand, and we take a much deeper dive in that analysis. And then we have another model that we look at potential procurement opportunities and risk mitigations, things like lifetime buy models and things like that that we build out that estimate how those risk mitigation techniques impact the sustainability of the system. And that is our conclusion. We can answer some questions. I'm going to stop sharing my video.
Thank you so much, George and Austin. Do we have any questions from the audience? If you have a question, by all means, drop it into the chat now, and we'll try to get that answered right here live. I'll say, George and Austin, this is, from my perspective, very impressive. It's really great to see the combination of the large scale model, which is sort of like a, finding outliers and pointing to outliers or showing some potentially high risk items that humans might not be tracking, and combine that with the deep dive or the more traditional item manager type review. That's really interesting to see the big data kind of coming together with our old styles or our traditional techniques of finding and dealing with problem parts. Has that been relatively successful over there? And have there been a lot of success stories with the large scale sustainment model bringing to light any parts or any issues that maybe the item managers hadn't yet been tracking?
Yeah, for one of our latest projects, an automation system, we've identified multiple parts that we need to analyze at a deeper level for sustainability. We have a short list of parts for the next tech refresh that are the basis of the justification of that next investment and the timing of that investment, and we're analyzing those in detail and coming up with some risk mitigation techniques. But we have identified a few parts outside of that list that are also high risk that really weren't on the original radar, and we've done some other deep dive models to estimate, do we need to do some lifetime buy procurements, or is there an ECP or a procurement of a like-for-like system that we need to test out, and when do we need to do that? So it's introduced those discussions for sustainment, and we continue to update that because that list will change over time, and usually, every 3 to 12 months, somewhere in that time frame, the data will change significantly enough that we can identify some potential new high-risk parts for that one system. Austin, is there anything you want to add to that, or thoughts?
I think that's an accurate summary. Yep.
Awesome. Well, thanks for that answer. Are any last call for any additional questions in the chat? Awesome. Well, George, Austin, thanks for sharing that. I'm going to take over the screen share here. Like I said, thanks again for that really interesting overview. Sustainment is something that all of us, really every weapon system we come up with, even satellites to some degree, require some degree of sustainment, although satellites quite a bit less than average. But it's really great to see the sort of, more traditional person in the loop, SME in the loop, combined with bigger data to help provide insight into sustainment, good, bad, or ugly parts, if you will. You know, every part that's not a problem is a result, just like every part that is a problem needs some extra attention. I have hopefully you can see my slides again, and I've dropped in the chat a luncheon survey. If folks don't mind taking a quick, it's a couple of questions, just takes a couple minutes, really helps us make sure that we're providing you the content that you're looking for and gives us some good feedback we can give to our presenters. And then, like it says there, we'll use this to decide our speaker presentation award for excellence. You know, as we always do, I like to plug the benefits of ICEAA membership. You know, really becoming a member really helps support the community and opens up a lot of doorways and additional avenues for folks that who can learn and get more involved in really helping shape their career and you know, showing that they're ready for the next level of cost estimating, and to really show that this is really a true career for them and something that they're passionate about. You know, in addition to opportunities like this luncheon, you get a lot of great subscriptions to ICEAA World, which has a lot of great papers and publications, a lot of great ways to get into the technical meat of our profession. There's also discounts into certifications and different exams that, again, can really help you improve your resume, show your professional commitment to this career field. And also there's a lot of options for additional networking and career events. And these are just a small list of the types of benefits you get from being an ICEAA member, particularly a member here in the Washington Capital Area chapter. As a quick reminder, is today October 1st? No, we've got September. We're a little over a month away from membership costs going up. So if you haven't updated your membership or looked into one of those longer term memberships, now is a really great time. Relatively often companies or organizations that employ you may be willing to reimburse those costs. If you're not sure, obviously you can check with your local POCs, but we at the Capital Area chapter do try to keep a list of who sort of will automatically pay those memberships for you, and you can drop us a line if interested. Also, I wanted to announce here this is the first time we've announced this publicly. We will be having our chapter all member meeting in just 1 month's time, the 29th of September. So we'll be having that at the Technomics office in Arlington, Virginia. We're going to have free food and drinks for members. There will be a fee for non-members because, again, membership is important. We're going to have a keynote speaker, Mr. Stephen Loftus from DASA CE. He's the Army's head of cost estimating analysis. Really eager to hear his thoughts and notes regarding the state of our career field and just his ideas of what cost estimating looks like in the Army. We'll also have chapter awards, kind of like National gives out awards each year. Our local chapter does give out awards to local members, and we definitely hope that, you know, we want all the award winners to come and be presented. It's going to really be a great opportunity to really feature and highlight some of the great work that local members have done. We'll also have a chapter year in review. What have we accomplished? What are we looking forward to? We want to hear from all of our members and make sure, again, we're giving you the type of information and the type of content you're looking for. Watch later today. There will be announcements that come out via email where you'll be able to RSVP and get additional information, but just wanted to make sure we use this opportunity as a place to note that that's coming up here in the next month. With that, I hope everybody enjoyed their lunch. I know I learned a lot about some awesome ways in which we can do cost estimating or ONS methodologies and business cases, and the use of big data combined with our more traditional SME knowledge. So I definitely want to thank George and Austin for your time today, and for everybody else for joining me. If there are any questions, comments, or concerns, by all means, reach out to us. You can get our information on our website, on our LinkedIn, or any number of ways. So with that, thanks everybody and have a good one.